right? And chapter 8 is kind of like a continuation of chapter 7. It's also a differential equation, but we are putting it in the form of an eigenvalue problem, right? And in I think in the chapter 6 or whatever, we have eigenvalue problem already. We talk about that, but that is more in the form of matrix. We put the equation, and assuming the equation can be put in the matrix form, which means you have your operator and get all the matrix element of the differential operator, and then put it in the matrix form and solve the eigenvalue problem that way. So that requires you to have a basis that have nice property. Most likely they are orthonormal. You can have orthonormal basis to expand your function and your operator and change your eigenvalue problem to a matrix eigenvalue problem. That is fine. And you can solve it this way. And this chapter is just to illustrate the property of this, the form of the differential equation and the choice of your scalar product. Remember that when we introduce the scalar product, we write a form, say, like we have f and g. Or in the integral form of the scalar product, we say that you can say integrate that from two endpoints and then f complex conjugate in g, and with a possibility to multiply by a weight function of x. Define your scalar product here like that, and but we didn't talk about what the choice of the w and why you should have w when you need for what differential operator you need the w, or what w that you need. And this chapter is just basically to illustrate that point. It's mostly about this point. And the idea is the w is to you choose a w so that your differential operator, once you convert that to use your scalar product and use it to solve an eigenvalue problem, you want that operator using this definition of scalar product becomes permission, right? Or self-adjoint, using the language of operator self-adjoint. Because in chapter 6 we talk about Hermitian operator using matrix, and we show that all the eigenvalues are real, and then the eigenfunction you can choose a set of all the eigenvalue can form a set of normal basis. That is important in solving the eigenvalue problem, right? And so we'll illustrate what this w depends on your form of your equation, and the general form of the equation for this chapter is you chosen differently. But first, there's 8.1 is a boundary value problem for a differential equation, which is just a simple harmonic oscillator equation, and the solution actually using Fourier series that we already talked about because we changed the order of our schedule. So we already went to Fourier series. So that 8.1, the equation should be familiar to you and how you solve it. So basically, you're using the Fourier sine series or the sine term for this problem. So we don't need to go through that because we've already done that. Okay, and now for the section 2, the form of your differential equation. L psi is, I mean, the eigenvalue problem is L psi is lambda times lambda is the eigenvalue. We want to find eigenfunction psi with eigenvalue lambda. So that's the eigenvalue problem, and then the differential operator L is given by this p little p x and d square dx square plus, actually it's p sub 0, p sub 1 x ddx plus p sub 2 x. So it's a little different compared with last chapter, because in the last chapter we choose the coefficient of the second derivative to be 1, and the second term is p, the capital P. So and the third term is q, and set that to 0 for homogeneous function, so homogeneous equation. So L psi is 0 in that case. And compare with this, then obviously this capital P, where P is used, is P1 over P sub 1 over P sub 0, and Q will be P sub 2 over P sub 0. Right? Using the old language will be this one, but in this chapter we use this one because the first case we consider is so-called self-adjoint condition. The condition is that P sub 0 pi is equals to P sub 1. Right. This is just one condition for genuine P sub 0, P sub 1, P sub 2. If this is satisfied, we call it self-adjoint. And in this case, obviously, you can say that you change the P sub 0 pi. Right? P sub 0 change to the P sub 0 pi. You can combine the first two terms into like ddx, P sub 0, ddx. That's P2. Right? You can see that this is the same as this if you just work out the derivative. So first you take a derivative over this derivative operator, so this becomes d squared dx squared. That will give you the first term. You take a derivative over P sub 0, you get P sub 0 pi and times ddx, and P sub 0 pi is P1, so you recover this term. Okay, so that is just, that is not the general properties, because P sub 0, P sub 1, P sub 2 can be general. So this might not satisfy. This is just, if this is satisfied, you can write the differential operator this way, and we call this self-adjoint. And what this means is that the scalar product in here, you can use the definition without the W. You can use the original definition of the scalar product. And we can see that right away. We can just work out a little bit. You can follow the textbook label. Instead of F and G, we use V, U, and V. Now, if this is V, this is U. Let's just write it down. V, U. Right. No, I actually take that back. We actually want, what we want is to illustrate a self-adjoint using this scalar product. So we want a V here, and take the scalar product with L operator on U. Okay, L operator on U. Remember this by the definition. This is the same as the adjoint operator on V, and take the scalar product with V. That is the definition of the adjoint operator. And we'll see that that would be the case for this definition of scalar product without W, because that is substitute that in here, complex conjugate, and the LU, and then you for a self-adjoint case, you use this one. So it's ddx 0 ddx. That operates on U, right? And then plus B sub 2. Right? And Now for the second term, of course, obviously is trivial because it's just multiplying u and v complex conjugate, and that you can easily interchange the order of v, u and v. Right, and so we just need to work more on the first term. That because this is a total derivative, you can. I mean, for this one, you can do a integration by part. The integration by part will be v complex conjugate v sub 0 u integrate. I mean, evaluate at limit a and b. Right? And then for the first one, you have a minus. For the second one, you need to keep the a and b. For the first term, you get minus p sub 0 u, and then v star x, right? Plus t, right? You just do one complex integration by part, get into this one, right? The second one is again doing integration by part using this du dx again, right? That will give you, first you keep this term, and then for this one you are minus v sub 0 v complex conjugate dx and times u. Evaluate a to b, and plus this, the integration by part of that is will give you u dx v sub 0 v complex conjugate dx plus v 2u. Right? Do you see that? Right? Now you can see that this term can be writing using the same differential operator, right? And to require to be self-adjoint, you will need the boundary term to be 0. And that is the usual case that we consider, although it's not always. Sometimes you want to keep the boundary term, but mostly we'll consider a situation where the boundary terms are 0. And we see that the cases that you can have the boundary term to be 0. First, it's a if p sub 0 is 0, of course, that is not good because that multiplied the second derivative, so you don't require that to be 0. And the second one is, second possibility is the value of the function is 0. All these functions, f and g or u and v, are 0 at the boundary, so that would be what we call the Dirichlet boundary condition. If u are 0, v are 0 at both ends, then that would be 0. The other possibility is the Neumann boundary condition. Du dx is 0, dv dx is 0 at the boundary, then that is, the boundary terms are also 0. So assuming either Dirichlet or Neumann or even mix of them, that can be 0. Right? And then that the situation, just go back to here, so that is equals to a and b, and you get the u out, and this is L operator on v complex conjugate. Right, and that is just, this is complex conjugate, and that is just L u u. Right. Is okay? So that is just using our definition of your scalar product with delta W. So start out with V, L times U, L operator on U, you end up L operator on V. If the scalar product will be U. And right, you can see that, right? So this is just, you're just changing the order. So this is your, the term that go into the left-hand side. This is U, right? Right, and if this is equals to that, then by our definition of an adjoint operator, that means L is equals to adjoint. What symbol do we use for adjoint? Dagger, is that dagger? Oh, dagger equals to L. This means self-adjoint. Okay, so this condition is consistent with, we said this is a self-adjoint condition, and now if you use this definition of scalar product with delta W, then we show that this is true. Okay, so that is the case. And now we go to the next discussion is if the operator does not satisfy this. Well, originally you have P0, P1, and P2. If it doesn't satisfy, we want to make it self-adjoint. And the way to make it self-adjoint is to introduce this W parameter into the definition of your scalar product. Okay. Just need some space over there. I still have some space over here. Right. All right. So basically, how much time do you have? Oh, it's already time. I have time to do that. So we'll do this that part next Monday. So make it self. If this is originally not self-adjoint, multiply by W to make it self-adjoint. But I need to stop here. But any question up to here?